Okay, you have any questions? You sure? I want to talk a little bit about some of the terminology we've got here. We have this very simple differential equation up here, dy dx equals 1. Of course, that's just saying y prime equals 1. So to get you'd solve this just by taking the antiderivative, 1 dx, and that's going to be what, x plus a constant. Now, depending upon what constant you have, you're going to have different, in this case, different lines. But any function of this form is going to satisfy that differential equation. So in particular, any real number we put in for c will be a different function that satisfies this differential equation. So one of the ways we're going to say that is this constant that we pick up at integration, we're going to call that a parameter. And there is one constant of integration, there's one parameter. So the way we're going to call this is y equals x plus c is a one parameter family of solutions. So c in this case is any real number. So the parameter just means the different constants I put in give me different solutions. In this case, they're just very simple little different lines. But each different value for the c gives me a different solution. Okay. And you might have, if you were taking if you're starting with the second derivative and working your way backwards, each time you'd find an antiderivative, you pick up a constant. So you might have, in that case, two constants. You'd have what's called a two-parameter family. Okay, this is number 16, page 14. We want to show that this equation, x squared plus cy squared equals 1, is a one-parameter family of implicit solutions to this differential equation. So in other words, you put in different values of c, you give a different equation here, but it will always be a solution to the dy dx equals xy over x squared minus 1. So this is implicit we're talking about, so let's do the implicit differentiation. So take the derivative with respect to x of both sides. Okay, this one isn't too bad because the derivative with respect to x of x squared is 2x. The derivative with respect to x of c constant times y squared, well, that's going to be the power comes out in front, 2cy. That's the power part. Now take the dy dx. And the derivative with respect of 1 is just 0. Up here. So we need to solve. So see if we can solve this equation and make it look like the dy dx thing we have here. So subtract 2x. Let's see, 2cy. Dy dx equals minus 2x. Divide both sides by 2cy. A little bit here. So we would get dy dx equals minus x over cy. Tell you what, let me move that up here. Well, that's not what we got. We don't have dy dx equals minus x over cy. Somehow I need to transform this fraction we have for dy dx into the one that they're asking us about, xy over x squared minus 1. Well, since the dy dx up here has a x times y in the numerator and not a negative, so let's multiply by minus y. Of course, if we're going to multiply on the bottom by minus y, I have to multiply on the top by minus y, I have to multiply on the bottom. So this gives me an xy in the numerator, which is what I want. Now the denominator says cy times negative y. That's going to be a negative cy squared. Let everybody catch up with me a little bit here. And you might think we're not any closer to where we started, but actually we're just about done. Because the solution we're looking at here if you subtract cy squared and subtract 1, so bring the cy squared over to the right, making that negative, bring the 1 over to the left, you have x squared minus 1 is the same thing as negative cy squared, which is good. That's what we want, xy over x squared minus 1. So by taking the first derivative implicitly and then fiddling with it a little bit, we were able to make the verify that this actually is a solution of that DE. Okay. So different, the constant kind of went away here, but different values of the constant give you a different solution. So you can put some positive values in, some negative values. You can put 0 in and get different different functions here, actually. Okay. So what I'm going to do is, let's take a look at that. So let's analyze x squared plus cy squared equals 1. Well, if c is equal to 0, it's just x squared equals 1. X equals plus or minus 1. Of course, that would just be vertical lines. I don't really think that would be a solution because that's not a function. Not y is a function of x, but we'll let that go. It's going to be something I'm going to graph here. How about if c equals 1? X squared plus y squared equals 1 is its graph of a circle. What about c? Now I've plotted some. That's what the shaded region over there is. What about c equals, let's say 4? We could put some other number in there, but c equals 4 actually would work kind of nicely. What is x squared? Plus 4y squared equals 1. What does that get? Well, it's an ellipse. So it's still round. It's just that the 4y squared, that's going to kind of squish it in one direction. But anytime you have an x squared plus a y squared, if they're both positive, equal to a positive number here, that's going to be an ellipse. Let's take a look at some negative values. If c equals negative 1, we have x squared minus y squared equal 1. Okay. What conic section is that? It's a hyperbola, yeah. And if you change negative values here, well, x squared minus 4y squared equals 1. That's still going to be a hyperbola. It's just going to be kind of squished up or stretched out in a particular way. So what I've done is I've got a nice program on my computer, and I graphed several of these to show you what this one parameter family looks like. See if I can enlarge that a little bit. The x equal 0 vertical lines are these two guys here. The positive value, x, when c equals 4, it's this little bitty ellipse in the middle. When c equals 1, it's the circle. When I did a 1/4 just to get an idea. It's the blue, the light blue ellipse. When c equals -4, it's this hyperbola that's kind of the dark red one. When c equals -1, it's the red hyperbola, and if c is -1/4, it's going to have this kind of a purplish sort of one that's not as skinny. It's much flatter than the other two. So these are what the one parameter family looks like. So what you should do is you should be able to recognize its circles and hyperbolas. And if you really had to, you could sit down and draw them. Although it's been a while since we did it in Calculus 3 for a couple of you. Okay, but implicit solutions, a one parameter family of implicit solutions to the differential equation. Okay. What we got next? All right. Oh, that's not ready for that yet. Yeah, I need to add a page in here. Not ready for that one. This says number 22. Page, what's number? Yeah, page 14. Okay. I'm not going to do the whole thing on number 22. The first part is to verify that phi of x equals c1 e to the x plus c2 e to the negative 2x is a solution to, this is a two parameter family because you got your two constants, to this second order dE, the second derivative of y with respect to x plus the first derivative of y with respect to x minus 2y equals 0. This is pretty straightforward. You just take the derivative twice and take the second derivative plus the first derivative and then subtract 2 times. This is your candidate for y. So take the derivatives and the original function, subtract 2 times that off there, and it just all adds up to 0. Okay. So it's not hard to do that. I'm going to skip that. Okay. Let's go to the part A of this. Is to where am I here? Yeah. Find C1 and C2 so that y of 0 equals 2, y of 0 equals 1. This is what's called an initial value problem. We've got our derivative. Of course, it's a second derivative, so you'd have to, if you're integrating it, you'd have to integrate twice to get back to the original function. And what we want is we want to find a solution. We've got a candidate for a solution here, and we want the one that actually passes through the point with when x is 0, y is 2, and when x is 0, y prime is 1. So what we're going to need is we're going to need y prime here because I've got y. Y is c1 e to the x plus c2 e to the minus 2x. So y evaluated at 0 is c1 e to the 0, c2 e to the minus 2 times 0 is c1 plus c2, and using this first initial condition, that has to be equal to 2. Okay. Pardon me for a second. I need to sharpen my pen. See, things look a little better here. So we need y prime. So taking the derivative of y, see the derivative of e to the x is just e to the x. So this is c1 e to the x. The derivative of e to the negative 2x is negative 2 e to the negative 2x. This is minus 2 c2 e to the minus 2x. Now the second initial value condition we've got here says when I plug a 0 into that, I should get a 1. So y prime of 0, c1 e to the 0, minus 2c2 e to the minus 2 times 0, c1 minus 2c2, that's equal to 1. So we need to figure out what these constants are. What constants will give us these two values at x equals 0. So we take these two equations, and we have two equations with two unknowns that we need to solve simultaneously. So let me get a little extra space here. It isn't going to take much. We need to have c1 plus c2 equal to 2, and c1 minus 2 equal 1. You can substitute, or you can do multiply the top by 2, and then add that to the bottom. The C2's go away, so 3C1 equals 5. C1 equals 5 over 3, and let's see, to get C2, C2 then would be, plug 5 over 3, I use the top one, 5/3 plus C2 equals 2, 2 minus 5/3, well that's 6 over 3 minus 5 over 3. C2 is 1/3. So for right now, you're just going to have to trust me that that really is a solution. You can verify it. And that's a DE we'll solve later on. It's not a hard one to solve. A second order linear DE is got a pretty nice little solution. If you remember the quadratic formula, it's a pretty nice little solution. Okay, so there's some kind of practical stuff. We're going to write up something on the board that's fairly theoretical here in a second. Okay. I haven't got my pages out of order. Let's see. Two big questions. When does a differential equation have a solution? They don't always have solutions. So we'd like to know if they do, or if something doesn't, we don't want to waste our time with it. Okay. Another question is, when does a differential equation have a unique solution? Sometimes there are different solutions that work. And in this next section, we have a theorem that answers that question to some degree. And it's rather theoretical. We're not about to prove it. It's a really tough theorem to prove. There will be times when it's impossible to find a unique, to find an explicit solution. So we'll have to do something approximate, maybe like you learned in Calculus 2. Did you ever do Taylor polynomials or Maclaurin polynomials? Or we'll maybe just try to get some sort of picture for it. So we want to know if it has a solution, then what can we do about that? So given a first order differential equation, okay, so first order means it just has the first derivative in it. dy dx equals something. So it's some dy dx equals some formula with x's and y's in it. I'm going to sharpen my pencil again. I don't know why it won't stay that way. We'd like to, okay, we're going to try to answer the question is when does it, oh, pages backwards. Here we go, yeah. And so we have a first order dE dy dx equals f of x, y. So it's just some formula of x and y. And we also have some sort of initial condition. There's a particular point in the plane we're interested in, x0, y0. Okay. So we want to know, does this have a solution? Is there a solution to this equation through this point? So here's some conditions. If and the partial of f with respect to y are both continuous in a rectangle containing this point in question, x0, y0, then there is a unique solution to the differential equation. Well, let's give this unique solution a name, phi of x in some interval containing x0. Okay, now we're going to do a little bit with partial derivatives, but it's pretty straightforward. What I'm talking about here, the partial of f with respect to y, just means take the derivative of f, y is the only variable, everything else just treat like a constant. And also, as far as continuity is concerned, we don't have, the functions we're going to be looking at are pretty simple, so we just have to make sure they're defined. We don't have zeros in the denominator or negatives underneath the radical or some sort of crazy skipping function or something like that. So as long as we have relatively nice functions, it'll be easy to tell whether something's continuous. So let's do one here. This is number 25. Actually, let me see if I've got this written down on the next page. Yep. 1425. And when I laid the pencil down, it got fat again. There's some way to keep the stylus with a thin mark, but I don't know. It's smartboard's hard to use sometimes. Okay. Now, the differential equation here is 3x dx dt plus 4t equals 0. Now, I don't have to do this, but I'm going to change it to x's and y's instead of t's and x's, because we're used to looking at x's and y's. And but let me finish stating the problem. Is there a unique solution? Is there a unique solution having x of 2 equal minus pi? Let's rewrite this in terms of x's and y's. Okay. X's and t's here. Of course, the independent variable, if I'm going to translate this back to y's and x's, the independent variable is going to be x, and the dependent variable is going to be y. So, in other words, 3y dy dx plus 4x equals 0. We're looking at when x is 2, y would be negative pi. Okay, so we have now the theorem had what? I'll do direction fields on the next page here in a second. So the theorem had dy dx equals f of xy. So in order to use the theorem, I have to write that, I have to solve for dy dx, because I don't have an f of xy on the right side. So okay, so solving for dy dx, I get dy dx is negative 4x over 3y. And that's my function, f of xy. We need to know is f continuous at this pointed question. Let people kind of catch up to me here. So f of my function, that's the right-hand side, the formula on the right, negative 4x over 3y. Is that continuous around the point? Well, where is it not continuous? The only place f is not continuous is when y equals 0. Because that would give me a 0 in the denominator, and we're not near that. So f is continuous at negative 2 pi. Now we also need to know about the partial of f with respect to y. So what's the partial? If we take the derivative of this thing with respect to y, so that just means, as far as we're concerned, x is a constant. The only variable there is y. So what's the derivative of that thing? I don't want to use quotient. But I mean, x, 4, those are just constants as far as y is concerned. So it's just negative 4x over 3 is, since there's no y's in that, that's just a constant. I'll bring that out. We just need to take the derivative of 1 over y. And think that's negative, this is y to the minus 1, so negative 1 over y squared. Let's see, this is going to be 4x over 3y squared. And again, this is the partial of f with respect to y. It's continuous at, excuse me, not negative 2 pi, well it is, but 2 negative pi also. Because again, the only problem with it would be if the denominator was 0, because it's a fairly straightforward function. Okay, so we've got this differential equation. We looked at the function on the right, and it's partial with respect to y. Both of those are continuous at the point in question. So the previous theorem, which I think had a name I didn't write down, it's theorem 1. By the theorem, you have a unique solution. That's great. What is it? Who knows? The theorem doesn't really tell you how to find it. It just tells you whether there is one. Now this one isn't too hard to find. We'll use a technique called a separation of variables to solve this. But the theorem doesn't tell you really how to find it. It just says if these conditions are met, then you know there is a unique solution. So that's what we got. I know I got a unique solution at that particular spot. Now it doesn't tell us what happens other places, but actually, as long as we don't get too close to y equals 0, I'll be able to find unique solutions. But once I get at y equals 0, all bets are off. Okay. Because neither the function nor its partial are going to be continuous. Okay. Well, let me see here. I don't mean to do that. Okay. Now we're going to talk about, if we know we got a solution, how could we find it? Well, we might not be able to, so maybe we can approximate. We continue looking at first order differential equation. The derivative equals something. Okay, what's the first thing you learn? You learn calculus. What does the derivative stand for? What does it tell you? It's slope of the tangent line, right? So if you evaluate this, say f of xy, whatever that formula is, if you evaluate that at various points, then what you will get is the slope of the tangent lines at different points. Not just tangent lines to the solution. In other words, if I want to do an example now. Yeah, I'll do this one. I'll do this one in more detail here. For example, dy dx equals negative 2x over y. This too is something we could solve, okay? But we're just going to play around with it, pretend like we don't know how to solve it right now, but we'd like to know what a solution looks like, even if we might not be able to find an explicit solution here. Okay, so at the point 1, 1, okay, if we plug that in, dy dx is negative 2 times 1 over 1 equals negative 2. What this means is the solution to this differential equation, which passes through this point, has slope negative 2 at 1, 1. In other words, if I went over here to 1, 1, there's some solution to the dE at that point, and that's what its tangent line looks like. So the solution might look like that, or the solution might look like that, or some kind of combination that way. I just know at that particular spot, the solution to the dE has slope negative 2. So just knowing just looking at a little piece of the tangent line there gives me an idea of what the graph looks like at that spot. Now, if you do this same thing at a lot of different points, like a grid of points on there, then you get what's called the direction field. So it is evaluate the dy dx at a grid of points and plot little tangent slopes. The calculator program I gave out the other day, which is titled Slope Field, is the same thing as a direction field. So what I did is, and since I can't make my calculator work right now, let me see. Do I have it here? There it is. Magically appears. I wasn't sure I'd be able to actually reproduce that. When you use the slope field program on the calculator, okay, you need to type that program in. You put in for y1, you put minus 2x divided by y. I have set this up so that the graph I have copied here is from, I think, negative 6 to 6 on the x, and negative 4 to 4. If you want your graphs to be pretty much the right scale, the right aspect, you need the height to be about 2/3 of the width. What we found here, here's 1, 1, that's that guy. And what you can tell by looking at this is that probably solutions to this thing are ellipses. Now, if you're going, you can use the direction field to sketch, a guess as to what a solution looks like. And the idea is not to go through these lines, but actually to be you're just kind of taking a suggestion. A solution would be kind of like tangent to these, some of these. It wouldn't. Like that. Okay. So even if you don't have the equation of the solution, you can get some ideas what its graph looks like, and maybe guess. Or when you actually do get a solution, you can check to see if it matches up the slope field, the direction field. This is number 2, page 21. The book has a much better graph than I do. This is just what I copied off my calculator. So you should look at the book's picture because it's a lot better. what they want us to do here is the differential equation is dy dx equals 2x plus 1. And actually I've got the same thing from negative 6 to 6 on the x and negative 4 to 4 on the y. And they want to sketch the solution curve that passes through negative to 0, negative 2. 0, negative 2 is, oops, right there. Okay. First, let's figure out. You got to pardon me, the board's got out of line all of a sudden. Okay. So at 0, negative 2, dy dx equals negative 2. So that's your tangent slope. That's at the red spot I have there. We're asked to sketch a solution curve that passes through that. So it's got a slope negative 2. So at that particular spot, it's going down, and it looks like it probably would do something like this. Still not. Something kind of like that, maybe. Okay, you're not going to do a great job on these. Should get a little closer. Should match up a little better. Then they ask a question which I don't know how to answer. From this sketch, write the equation for the solution. When I first saw this, I thought they might be talking about, well, maybe this is a parabola, but a parabola, this direction field doesn't look very symmetric to me. It looks like it's steeper on the right and not so steep there, which wouldn't be a parabola. So I don't know what they mean by write an equation. So let's just say that. I noticed that none of the other questions ask you to do that. They ask you to sketch a curve, but they don't ask you to come up with an equation for a solution. All right, so for part B, we're after sketch the solution curve that passes through negative 1, 3. Okay, so let's plug that in to figure out what the slope is. X is negative 1, y is 3. So it says negative 2 plus 3 equals positive 1. Negative 1, 3 is about here. Smart board put it a little bit high. Anyway, it's not about there. It's a little bit further down than that. Negative 1, 3 is about there, and it's a positive 1, so it's actually going up at that point. So it would be something like that. Again, if you use the grid in the direction field in the book, it's a little easier to draw because it goes up further. Okay. It looks to me like this particular direction field, all the solutions look the same shape. They just kind of shift, kind of going down in a little bit of a diagonal. This just keeps being the same sort of whatever it is going down. Okay, so now they ask a question too about this. What can you say about the solution to this? Part B, as x goes to positive infinity or x goes to negative infinity. Well, it doesn't show up very well on my picture, but the one in the book, it looks something like this. So as x goes to positive infinity, I'd say the solution also goes to positive infinity. And as x goes to negative infinity, we're off this direction. I'd say, again, y goes positive. You see that because the little slope, the little tangents, get more and more vertical as you go from to the left or to the right. Well, I'm going to stop there. I've got a few more to do here and a few to assign. I'll tell you what, let's do number 10. Oh, my calculator doesn't work. I'll figure out what's wrong with the calculator on there. I have this thing programmed on my little calculator, the hand one, but I can't show that on the screen. So I'll do a couple of more of these next time. And we're going to get out extra early today. But let me give you some to work on here. (21) number 5. 6 and 10A. Now, when it says use a computer software package, you can certainly use that program on your calculator. I don't know how you're going to get it to print. One of the things I did, which doesn't show up here, is I do have the TI-83 calculator on my computer, at least in my office, and it runs this program, and that's what I copied and put on there. So you could always, if you had the virtual computer on there, you can always just cut and paste that on in a Word document or something like that, and then draw on it yourself. Unfortunately, I can't get it to work here. Try it one more time. Nope, it worked in my office. It worked in the room next door, but not today. Okay, any questions? Okay. Got some stuff to hand in? Great. Yeah. What was it, just the first? Yeah. Yeah. So you've got other stuff and this to be working on, and yeah, and that'll be next Tuesday. I mean, 1321. Like I said, I got 2 more examples to do on page 21. Yeah, we'll put them in there. I'm getting a little bit overwhelmed on some stuff, so I don't want to take up things Thursday. Got to catch up in my other class. So this 13 and this stuff on 21 for next Tuesday. And get this program in your calculator. Works nice. It's a lot of fun just to fool around with, just to see what sort of interesting patterns you can come up with.